Good morning, ladies and gentlemen, and thank you, David, for the very nice introduction. And so here, my talk comes with spectral variation classification robustness with factors in the measurement circumstances. Yeah, when the hyperspectral data is measured, right, there's a lot of factors come in play. For instance, the sun is keep moving and the ground moisture is ever changing. Well, maybe once study area with topography effects, autumn shadows. And thanks to the previous talks, you have already know that their variations are quite important and they are there. But well, there's more problems for researchers who are using those data that how much of your data is measured, is affected in the measurement procedure, and what are they looks like, especially when you only have like single data source. And then there's another question like, well, the calibration itself brings more effect in your data, and then there's this complexity will be passed step by step to your end use. And then if you have multi-temporal data, how do you classify them robustly? So to seek these problems, I did some tests. The first one is on the changing illumination zenith. Why I'm doing that? Because it's a very common factor you're going to face when you're using like data from multi-source, aster, arrays, something you want to merge them together. They always have different observation geometry, right? And then if you are measuring on some very topographic area, you have complexity illumination, or even you are just measuring a vertical object like the mining walls. So to collect the data with the changing illumination zenith, we set a lab experiment to simulate it. We used 7 pure mineral powders and 1 ASD spectrometer. We use a halogen light as a light source, and then we change it from the 5 zenith angle, which is near to the direct normal, and then in 10 degrees every step, we move it to horizontal at 85 degrees. In this process, for each sample, we measure 9 spectra and take the spectra from the kaolinite here as an example. You can see there are 2 main effects caused by the changing zenith. First, it's getting more and more noisy, which is quite common, I think. But what is not out of my expectation is that the spectral brightness seems keep increasing with the zenith go down. Why it happens? We think it is because the white reference panel we use at calibration, it's not working with so much diffuse reflection when you lower the zenith. Well, our sample are powders, so the reflection comes underneath those powders, and when the light goes near horizontal, they have more diffuse, so the light goes into the sensor. And then we classified all the measured spectra. To visualize it, we transferred all the spot spectra into the data cube. We use the 3 classifiers to do that. Spectral angle mapper works solely on the spectral color, and Euclidean distance classifier works on both spectral color and brightness. And also I developed an expert system to classify it. Well, the result is a little bit out of my expected good. So the results you see from the top to bottom, every row is filled with spectra measured from these minerals, and from left to right, there are the spectra measured and the different zeniths. And spectral angle mapper works perfectly with all these pure mineral powders. Well, Euclidean distance is a little bit a mess, but it only give you misclassification and the almost the horizontal zenith. Well, we all see that one main effect from the changing zenith is the brightness, and this poor guy works on brightness. And my expert system is designed based on the center position of mineral diagnostic feature. And this boronate feature is quite shallow, so it's easily disturbed by the noisy level, the high noisy level at the near horizontal zenith. And here comes my second test it. I tested the factor. This is a effect of moisture. Why am I doing that? Because, well, on the ground, moisture is ever changing first. And besides, the drill core or some the mining phase are always wet. So I think it's also quite important to collect the data. We also simulated an experiment of increasing moisture in laboratory. This time we used the halo spot spectrometer on 6 different pure mineral polymers. We measured the samples from a totally saturation to oven dry in steps of approximately 5%. And in this study, we defined the moisture content as the mass of water divided over the mass of the whole sample, right? And here take the, well, a spectral measured from gypsum as an example. You see here, there are 3 main effects from moisture can be observed. First, it's getting darker when the water are increasing in the sample. And second, the OH features, they get to spreading with more and more moisture content. So the mosaic or dominant those diagnostic gypsum features here and here. And last but not least, when I add water into the samples, I artificially create a spectral mixture, right? So with more and more amount of water in that, you can see the mineral diagnostic feature of gypsum are not that big and deep again. But even though the center position possess a quite consistent wavelength position over there until you really have a very high moisture level, and then the whole feature is disappeared. And afterwards, we classified all the spectra in the wavelength range from 2100 to 2350 nanometer. Still similar to the first study, we classified them using the spectral angle mapper, Euclidean distance, and expert system. To visualize it, we also transferred the spot spectra into this data cube. And from the result here, you can see first the moisture damaged the result much more than the zenith. And besides, if you look at the overall robustness, the classifier selection plays an important role on you classify them with changing moisture. The expert system achieves the 90% of the robustness, while the poor EDC only has a 40% because it works on brightness. And I also put all these numbers on top of each column. Each column is a contains spectra measured from each of my 6 samples. And these numbers means under which moisture content the spectra from that sample is misclassified. And therefore you can see, well, the type of mineral itself plays a role in the mineral classification. This is haven't been published paper, and we are in the final stage before sending it out. So if you are interested about details, there's a QR code. Wait how I hope there's a 2 or 3 months you can see all the details on the paper. And subsequently, we think that our first 2 studies are based on live measurement spectra from the polar samples, and we like to test the knowledge we gained from the first 2. So we designed an experiment to measure spectra outdoors from the solid materials. And therefore, we conducted this SpecIM sphere camera mounted on the track and to measure spectra from rock over the whole day on this year, 7th of July, from 10 a.m. to 6 p.m. in time interval of half an hour. And so we get a solar altitude change from 40 degrees to 60 degrees. And what we measured here are 2 rock types. First is marble, and then we have basalt. So one is very bright, one is very dark. And we shaped all this, you can see the rock split as a pyramid shaped on the tree. And we built 2 pyramids out of each rock. And for one of them, we spray water on that. So we get a lot of parameters here to compare. And we, after the experiment, we do more data processing on image took on straight time at 1125, 1370, sorry, 1337, and 1531 to as examples to show what the problem can be. So the first way to do it is to see spectral variation. We averaged spectra out of each slope of a pale over the 3 time. And here take the measurement from the marble pale as examples. You can see the right part is a white marble, and this part is sorry, the right part is a dry marble, and the left is a white marble. And the top 2 figures contain spectra measured from the slope 1 and 2 from the dry marble over the 3 time. And not the blue line over there. The blue line is measured using a halo on the same sample, but indoor. So that's a reference spectra over there. You see the main problem is looks like the brightness also changed with the sun moves. That is quite common. And besides that, for spectra measured from the slope number 2, we see a more and more shallow carbonate feature. Why it happens? Because this slope is covered too much by the shadow. And when the sun azimuth changes, it covered more and more part of the shallow. And well, the shallow spectra is quite dark and flat. So when I average spectra from all this area, the shallow curves that. And the bottom 2 figures are spectrum averaged from the wet marble pale. You see the variation trend is quite similar with those from the dry marble. It's only, the water makes it darker. And besides, we found some more clear, small absorptions around this carbonate feature, which I still need to work on to figure out what they are. Afterwards, we also classified the spectral image using Euclidean distance and spectral angle mapper. So still the 3 time, you see those yellow arrows over there to indicate under which solar direction I measured this image. And before classification, we do a spatial subset using these white rectangulars to avoid age and the sample containers, and then we mosaic them together as a classification base image. The end member used only 2 end members. They all averaged from the dry marble pale and the dry basalt pale. And the results shows that quite different. The Euclidean distance misclassified considerable amount of marble as basalt. And you see those pattern of misclassification, they associated with the change of the solar movement. So I have the confidence to say they should be caused by the shadow. And when the pale is wet, the thing are even worse. This is because both the shadow and the water cause very dark spectra, and basalt has a rather low spectral brightness, and our poor EDC works on brightness. But the good part for it is the basalt is quite robustly classified out of the same reason. And for the 3 images from the right, they are results from the spectral angle mapper. On the contrary to the results from EDC, it's robustly classified marble pale because it considers only the color, and marble, as I showed before, even we have effect from geometry, shadow, moisture, everything, but carbonate feature is still there, quite consistent. The only problem for it is that one misclassified many pixels of basalt as marble. And you can see there are also, if you clearly see that the pattern of misclassification also in a bit association with the solar direction. I think this is because when the more shallow is on the basalt pale, that one gives less reflection energy, right? So it's more noisy over there, and some of the noisy peak is misrecognized by spectral angle mapper. They think, okay, you have a shape at 2300 nanometer, that's a carbonate. And but you do anyway. So still, the classifier selection plays a role in the robustness for her. Here comes my preliminary conclusion. That's as I shown before, the fixed factors of changing measurement circumstances, they affect your result in every step of the whole hyperspectral processing chain. But even with this, with a proper selected classification strategy, you can still produce your data quite robustly. Thank you very much.